Okay, good evening again, everybody. So welcome to meeting number 4 of Math 211. So for tonight, we will be going through the part of the module that talks about vector spaces. Now, last time we talked about the notion of fields, right? So again, I think we spent 2 meetings to talk about fields, what are the requirements for a set F, together with two operations, addition and multiplication, to become a field. And I think in the homework, you tried proving that certain sets, together with some crazy operations between their elements, are indeed fields, right? And then we look at the properties of the field, and hopefully there through that session we did last time, you were fresh on how to write mathematical proofs. And that will be very crucial, not only for the first set of homeworks, pero hanggang sa dulo na ng course. Kasi yun talaga ang bread and butter of a mathematician, or in a mathematics course, you will do lots of proving. Contrary to popular belief, na probably we have experience from elementary and high school that math is about computations. But if you go to higher mathematics or advanced courses in math, such as Math 211, mas marami tayong proving. We're answering questions like why and how rather than what is, right? So hindi tayo nagko-compute, mas nagbibigay tayo ng dahilan kung bakit totoo ang mga iba't ibang mathematical ideas or mathematical statements. So that's what we did last time. Hopefully that helped you working with the homework. Now, hindi tayo masyadong magtatagal sa konsepto ng fields because this is really something in the domain of abstract algebra. So, nasa na kayo sa abstract algebra? Nagsimula na ba kayo ng groups, rings? Hindi ako familiar sa outline ng 211 eh. Anong 2, what's that? 210.1? Hello guys. So, monologue ba ako buong gabi ngayon? So, nasa kayo sa 211? O yata hindi nakikinig sa 211 nila, oh. 211, hindi pala 211. 210.1. Ayaw talagang magsalita. Pero naririnig niyo ako. I hope you can hear me. Ayan, thank you, Aline. Pero ayaw niyo mag-comment about, ayaw niyo mag-comment about 210.1. So that's fine. But essentially, fields is really in the domain of abstract algebra. So if you want to learn more about fields, saan sila ginagamit, what are their mathematical significance, dun niyo siya matututunan sa abstract algebra. But in this course, I just needed to talk about fields para mabuo ko yung konsepto ng vector spaces. Because if you remember, in a nutshell, Math 211, as I mentioned to you before, is the study of linear transformations between vector spaces. So ano yung mga functions na may linearity property mula sa isang vector space papunta sa isa pang vector space. Now, I cannot start the discussion of a vector space without talking about fields. Kasi yung fields, sila yung magiging scalars doon sa ating vector space. Right? And now, I think this is a good time for us to look at the definition of a vector space. And that is definition number 3 in the module. All right? So let's look at definition number 3. I hope you can see my screen. Flashed is the definition 3 for vector spaces. So kung mapapansin nyo, the first sentence starts with having a field. So we're assuming meron tayong field F before tayo makapag-define ng vector space. Then after we have that field in mind, we will consider a non-empty set V together with two operations. All right? So parang field din, dalawa yung operation ng isang vector space. Kaya lang, kakaiba yung dalawang operations na kailangan para magkaroon tayo ng isang vector space. Una, meron tayong tinatawag na vector addition. Vector addition, kukuha ka ng dalawang vectors kukuha ka ng dalawang elements ni set V. Hindi ko pa pala dapat ginagamit yung term na vectors kasi hindi ko pa na-establish kung ano yung vector space. Pero again, we start with a field F, tapos we get another set V. All right, a non-empty set V. Now, on the non-empty set V, we will define a vector addition. Kukuha ka ng dalawang elements ni V, sila yung ipag-add natin para makakuha ng isa pang member ni V. So you take, say, V at saka si W na element ni capital V. Pag pinag-add natin sila, kailangan element pa rin siya ni capital V. All right? That's what we call vector addition. So vector addition is just an operation defined on two vectors. All right? Vector to vector yung pinag-add natin. What is that addition? We don't know. We're just calling it addition. It might be different from the usual vector addition that you learned in college. All right? Tinawag ko lang siya ngayong vector addition. Ang vector addition, kukuha ko ng dalawang elements ni V, dapat yung sagot na kay V pa rin. Right? And then I need a second operation. That second operation is called scalar multiplication. Anong kaibahan nito? Kasi sa scalar multiplication, ang dalawang pinag-ooperate natin ay hindi mga vectors. Isang element ni field at saka isang element ng vector. Tapos ang sagot dapat ay isang element ni V. Alright? So halimbawa, meron kang field element, tawagin nating alpha, ita-times ko siya sa little v, which is an element of capital V, dapat yung product na yan ay element pa rin ni capital V. So the two operations that we have, a vector addition, which operates on two elements of the set V, and scalar multiplication, which operates on an element of the field and an element of capital V. Right? Is that clear? So magkaiba sila. Wala tayong vector multiplication. Meron lang tayong vector addition. So addition ng dalawang elements ni V at saka scalar multiplication, element ni field times element ni V. All right? Now, yun yung structure natin. Non-empty set V, a field F, and then two operations, vector addition and scalar multiplication. Just like fields, meron dapat properties na masatisfy yung dalawang operations na dinefine natin dun sa V at saka sa F. All right? The first property is associativity ng vector addition. So the ordering, or the grouping rather, of the elements as we operate under vector addition doesn't matter. All right? So yung V plus W plus Y ay equal lamang sa unahin mo yung V plus W plus Y. So ordering doesn't matter. Second is commutativity. The ordering doesn't matter. Mali ata yung nasabi ko kanina. The grouping dapat sa associativity. So commutativity, the order doesn't matter under vector addition. So vector, V plus W must be equal to W plus V. Dapat totoo to sa lahat for all V and W in capital V. And then third, there should be an additive identity or an identity under vector addition. We should find an element of capital V that will act as the identity under vector addition. That means if I add that element E sa kahit na ano pang element ni capital V, dapat same yung magiging result ko, right? So if I take any element of capital V, say little v, so say little v plus that additive identity must be equal to little v, right? So additive identity under the vector addition. Now, there should also be property number 4, additive inverses for all elements of capital V. Ibig sabihin, if I get an element little v, all right, dapat may mag-exist na isa pang element ni capital V, we'll just write it as negative V. All right? So negative V yung itatawag ko dun sa element ng capital V na pag inad ko kay little v, ang sagot ay yung identity. So parang kamukha pa rin to nung additive inverse na nakita natin when we were defining fields. Right? So meron siyang ganong property. Right? And then distributivity, pero may dalawa tayong klase ng distributivity na dapat masatisfy kasi meron kang dalawang operations, right? Pero hindi tayo basta-basta pwedeng mag-operate dun sa, hindi uniform. Yung pagkakaroon ng multiplication over a sum because we are dealing with two additions here. Merong vector addition at saka merong addition under the field. So kailangan i-distinguish natin ano yung distributive property na kailangan natin, and luckily, we are requiring two distributive laws to apply for a vector space to occur. All right? Una, dapat distributive ang scalar multiplication over vector addition. So if you are adding two vectors and decided to multiply a scalar to the sum, pwede mo raw siyang gawin, pwede mong i-distribute yung scalar multiplication sa loob ng vector addition. Alright? Nasa labas yung scalar multiplication, kaya i-distribute mo siya over the vector addition. Alright? So alpha is a scalar. It is an element of the field. So alpha, nanggagaling siya dun sa field. So, ipapasok mo siya dun sa vector sum. So, magkakaroon ka ng alpha v plus alpha w. So, this is required para magkaroon ng vector space. Right? Now, there's another type of distributive law that should apply here, and that is distributivity of scalar multiplication pa rin, pero over field addition. Okay? So, ibig sabihin, gusto kong ipasok yung scalar multiplication sa ibabaw ng field addition. So that means I need to perform, or I want to distribute or to do the vector, the scalar multiplication after I added two elements of the field. Right? So, pag kinumpare nyo yung distributive law A at saka yung distributive law B, sa part A, nag-add tayo ng mga elements ng V. Pero dito sa part B, nag-a-add ako ng elements ng field. So meron akong field element alpha plus field element beta. Gusto kong gawin yung scalar multiplication over the sum of the two field elements by a vector V. Right? So pwedeng, ang sinasabi ng distributive law B, pwede mong i-add muna yung scalars, tapos yung sagot i-multiply mo kay V. Right? Or there's another way to do it. You can distribute the scalar multiplication sa loob ng field addition. So you can do the scalar multiplication alpha times V, then add the answer to the scalar product of beta and V. So para talagang pinasok mo lang yung scalar multiplication sa loob ng field addition. Okay? That clear? So medyo mas matrabaho pala to ng kaunti kaysa dun sa fields. Kasi dalawang scalar, dalawang distributive laws yung kailangan nating i-check. And I hope you see the difference between the two distributive laws that we are dealing with, right? And then meron pang dalawang properties. These two properties are isolated for the fields for scalar multiplication. All right. So dapat associative daw yung scalar multiplication. So that means you can either multiply the field elements first before multiplying it to the vector, or you do it the other way around. Take the scalar multiplication one at a time. I mean, you multiply beta and V first, and then you get a vector here, then you multiply it to alpha. So pwedeng field times field element or scalar times vector yung pag-atake. So that should be true for a vector space. And the last property is that there should be an identity element with respect to scalar multiplication. You should be able to find a field element that will do nothing to all elements of V in terms of scalar multiplication. All right. Now, just a matter of abuse of notation here, the one here is not necessarily, of course, I hope you are already getting the hang of it, that this one is not necessarily the number one that we know. One is an element of a field capital F, right? But this one is not necessarily the unity in F. It is not necessarily the multiplicative identity of the field F. But I think we can prove that, or that's almost always the case. But the one here is essentially the identity with respect to scalar multiplication. This one should preserve the identity of the elements of capital V after scalar multiplication. Right? So C1, siya yung element ng field na pag minultiply mo sa kahit na anong element ni V, ang sagot ay yung element pa rin na V na yon. All right. And then if all of these 7 properties hold for a particular set V and a field F together with the two operations, vector addition and scalar multiplication, then we can say that V is a vector space. Tapos yung elements ni capital V, sila yung mga tinatawag nating vectors, at saka yung elements ng fields, siya yung tinatawag nating mga scalars. Okay. Is that good? Any questions so far? And I think some of you might be familiar with this definition kasi I know some of you had been teaching math for a long time now. So baka napagturo na kayo ng saan nga ba to? Kahit sa calculus, no? Meron tayong tinuturo na vector addition kasi kailangan mo ng R3, R2. Sa analytic geom meron din. So the same thing for vector spaces. Kaya nga lang dito sa Math 211, pinapayagan natin yung pagkakaroon ng mga kakaibang mga vector spaces. Kasi usually ang kilala natin sa undergrad ay mga vector spaces na puro mga numbers lang laman. Ang konsepto natin noon ng vectors ay isang arrangement of numbers, right? About 3 by 1 vector or 1 by 5 vector. So yun yung alam natin ng mga vectors. Pero ngayon nakita natin ang definition pala ng vector space, hindi sila kailangang listahan ng mga numbers, right? Katulad nung nasa R2, R3, R4. They are vector spaces pero hindi lang pala sila yung mga vector spaces. Kasi ang kailangan mo lang pala para magkaroon ng isang vector space ay isang field at saka isang non-empty set na may dalawang operations, vector addition and scalar multiplication, satisfying all 7 properties. So, makakita tayo mamaya ng mga examples ng mga vector spaces na hindi katulad or hindi nakaporma katulad ng mga vector spaces na natutunan natin nung undergrad. All right? But I hope everything is good. The definition is clear. Is that fine? Kinakabahan ako ngayon kasi wala nagre-react sa inyo, no? Okay, thank you, Aline. Yeah, Sol. Yeah. Yeah. Jennifer, you have a question? Wala naman. Magta-thumbs up lang pala si Jennifer. Kinakabahan ako pag walang nagtatanong, lalo na pag online classes. Kasi it's either of two things. Ano? Type 1 ay sobrang galing mo magturo at walang tanong yung mga estudyante. Alright? So kaya tahimik sila, nakikinig, etc. Or the type 2 is wala silang na-gets dun sa sinasabi ko kaya hindi sila maka-form ng isang sensible question. I hope it's type 1 na magagaling kayong estudyante at na-gets niyo lahat ng sinabi ko, alright, rather than type 2. But again, if you have some questions, feel free to ask me those during the class, alright? Okay, so let's see. What did I say here? This paragraph is just telling us a short history of vector spaces, that they are very applied in nature. The creation of the theory of vector spaces was attributed to non-mathematicians or those that are not purely mathematicians. Some of them were physicists, engineers that needed some tools to explain things in electromagnetism, in physics, etc. Kaya kinailangan nila ng konsepto ng vector spaces. Tapos kinuha ng mga mathematicians yan, generalized, and that's what we have now as the theory of vector spaces, right? Now, I'm mentioning here that we will adopt usual notations for vector addition. I think equation 10 and 14 are about how to write summation notation for vectors. Kaya lang, be careful when adopting those notations because, for instance, there's no such thing as vector multiplication. So yung notations equation 11, 13, and 15 in the module will not apply, all right? And then yung notation 12, we'll try to avoid it because that will be that can create some confusion with scalar multiplication. Kasi yung notation 12 yata ay a plus until a n times. Sabi natin, susulat natin to as n times a sa fields. Pero sa vector spaces, baka makalito ito kasi pag si a ay vector at si n ay scalar, baka iba yung interpretation ng n times a, which is adding a to itself n times via vector addition, than scalar n times vector a. So kaya hindi natin gagamitin yung notation 12 para sa vectors. All right? So, but I think the notations should not be should not be ambiguous here. It should be straightforward. So let's just clarify things as we go along. Tingnan natin yung mga examples ng mga vector spaces, all right? Now, in example 5, set R is a vector space over R. So this example is telling us that that our V is the set of real numbers, and our scalar, our field is R itself. At ito makikita natin ngayon na hindi pala kailangan yung usual quote-unquote vector na alam natin sa college algebra or calculus ang mga vectors. Kasi pwedeng yung set of real numbers, yung mga real numbers, pwede natin silang i-consider na vector din. Siya na yung set V, siya na rin yung field F. Alright? Na medyo kakaiba dun sa, kakaiba nga siya dun sa konsepto natin ng vectors na kung sa physics, di ba, ang vector ay isang quantity na merong direction. Kaya sabi natin, pag meron kang isang real number, hindi siya pwedeng maging vector or quote-unquote, hindi siya vector kasi wala siyang direction. Scalar lang yung tawag natin sila. But in theory, example 5 is telling us that you can get a vector space taking the field not only as the field of scalars, but also as the set of vectors with the same usual addition and multiplication, right? Tapos yung vector addition, siya na yung usual addition of real numbers, at yung scalar multiplication, siya na rin yung usual multiplication, right? So the proof is quite trivial because madaling i-check na nasa-satisfy lahat ng mga conditions, lahat ng kailangan dun sa definition. But sige, ano kaya yung additive identity? Ano yung vector? Again, the vector here, the set of vectors is R. The field of scalars is also R. So ano yung element ni R na nagsiserve na additive identity ng vector space? Anyone? What is the additive identity of the vector space of real numbers over R? Okay, kung ayaw nyo mag-unmute, you can use the chat box to answer. Just unmute yourself. Ano yung additive identity? Yes, Aline?
Hindi po to answer, Doc, but I have a question lang po. Yung vector ba sa algebra is same concept lang ng vector at scalar sa physics?
Mas general yung konsepto ng vector sa algebra kaysa sa physics. Kasi sa physics, ang vectors ay halimbawa yung vector ay 1, 2, 3, right? Ganyan yung itsura ng vector sa physics. This comes with the direction, etc. Pwede mo kasi siyang i-plot in three-dimensional space. Vector siya sa physics, vector pa rin siya sa algebra. So that's fine. Kasi nung inimbento yung theory of vector spaces, nag-start siya dun sa pangangailangan ng physics. So ganun yung vectors. So yung vector spaces sa physics, which is usually Rn lang naman, or n tuples of real number, or Cn. Kita natin itong mga examples na ito mamaya. Cn is n tuples of complex numbers. Nasa-satisfy niya yung definition 3. Lahat ng properties na nasa definition 3 ay nasa-satisfy nung vector spaces sa physics. Pero merong mga vector spaces na nakakasatisfy ng definition 3 na hindi kino-consider or hindi pinag-aaralan as vectors or hindi tinatawag na vectors sa physics. So parang mas marami tayong vector space, mas marami tayong pinag-aaralang vector spaces sa algebra kaysa sa physics. Kasi katulad nitong example 5, pag meron kang number 3, ano ba, number 3, baka sabihin sa physics na si 3 ay scalar lamang. Right? Kasi wala siyang direction. Hindi mo siya ma-plot. Pero sa linear algebra, pwede mo kasing tingnan, masasatisfy kasi ng set R, kung siya yung kukunin mong V, at si set R pa rin yung kukunin mong F, masasatisfy niya pa rin yung definition 3. Is that definition 3 or definition 2? Definition 3, right? So technically, yung mga real numbers, ito yung sinasabi ng example 5, yung mga real numbers, sila pa rin ay mga vectors din. Pero sa physics, hindi sila tinatawag na vector. Alright? Yan lang yung medyo pinagkaiba. Pero lahat ng vectors sa physics ay vectors sa linear algebra. Pero hindi lahat ng vector spaces sa linear algebra ay tinatawag na vectors sa physics.
Okay po, Dok. So, ang identity ba ng vector na to is, I mean, yung question mo kanina is the negative. Ang identity niya po is negative of the vector? If I'm not, kung tama ako, hindi ako sure.
Yun yung inverse. Pero ano muna yung identity? Ano yung i-add ko sa isang vector? At when I'm talking about vectors dito sa example 5, ang mga vectors ko ay real numbers. Ano yung i-add ko sa real numbers para hindi siya mabago?
0 po.
Yes, 0. Good, Aline. So ang identity dito, ang additive identity sa R ay 0, the real number 0. Because if you add the vector 0, which is the same as the number 0, sa isang real number, ang sagot ay yung real number pa rin na yun. So 0 is the additive identity in the field. It is also the additive identity in the vector spaces, in the vector space. Right? And then, tama ka rin, Aline, na dito sa vector space na to, ang additive inverse ng isang vector ay yung negative niya. So kung meron kang real number R, ang additive inverse niya ay yung negative niya. So because we get a 0. We get the identity 0, right? So kung meron kang vector 3, ang kanyang additive inverse ay vector negative 3. Kasi equal siya kay 0. Right? So I hope that clarifies things, and yeah. Though hindi to magandang example, gusto ko lang ipakita na ito yung pinakamadaling example. Pag may field ka in general, pwede mo siyang i-consider as a vector space over itself. Na yung set of vectors at saka yung set of scalars ay parehas yung field na yun. That's the easiest example of a vector space if we are coming off from the concept of fields. All right? Pero mayroon pang isang madaling gawin at ito na yung usual na nakikita natin na vectors sa physics. All right? Na pag meron kang field, kahit anong field, sige, dito ang example niya ay field of real numbers pa rin. Tapos kunin mo lang yung n tuples. So pag meron n tuples, sorry, I should be using this. N tuples of real numbers, say si V, siya yung n tuple consisting of V1, V2 until Vn. So tapos si W, n tuple din siya ng mga real numbers, W1, W2 until Wn. So yung vector space Rn over the field R. So ito yung ating V, non-empty set V. Ito yung ating field R. So real numbers yung field. Ang non-empty set V natin ay R to the n, which consists of n tuples of real numbers. Tapos ito yung vector addition natin. Ang vector addition natin, pag i-add ko si V kay W, ipapag-add ko lang yung first components nila, second components nila, hanggang sa nth component nila. So yan yung tatawagin kong vector addition. Okay? And then the scalar multiplication, alpha, so usually Greek letters yung ginagamit ko para dun sa scalars. So pag meron kang scalar alpha, which alpha is coming from the set of real numbers, times the vector v, which is this guy, all right? Ang scalar multiplication ay ganito lang. It times ko lang lahat ng elements, lahat ng components ni v by alpha. So alpha v1, alpha v2 until alpha vn. And then if we have these structures, v is Rn, f is R, vector addition is this, scalar multiplication is this guy, then we will get a vector space. Si R to the N ay isang vector space. Tatanungin ko pa sana pero na-spoil na nung notes na ang additive identity ay si 0, 0, 0. Kasi pag si V1, V2 until Vn ay dinagdagan ko ng 0, 0, 0, 0, ang sagot ay si V1, V2 until Vn pa rin. Right? So that means this vector here will preserve the identity of any other vector under vector addition. That's why this guy is called the additive identity. And usually we call this the zero vector. So yung additive identity, tawagin kaya natin siyang zero vector. Yes, Rose.
Sir, pasensya na po, late lang po ako nakapasok po kanina. Kanina
okay
po, you were mentioning about kung kailan lang po tayo magkakaroon ng vector space. Hindi ko lang po nakapasok yung two conditions, sir.
Yeah, yung conditions para magkaroon ng vector space. Yeah, it's definition number 3 in the module. Ito sila. Medyo marami kang dapat i-check, right? So kailangan associative yung vector addition, dapat commutative yung vector addition, dapat may additive identity, or this is what we're calling the zero vector. Meron dapat isang vector na pag in-add mo sa kahit na anong vector ay ang sagot ay yung vector pa rin na yun. Then dapat lahat ng vector may inverse under vector addition. Alright? Meron dapat vector kang makita na pag in-add mo sa isa pang vector, ang sagot ay yung zero vector or the identity vector. Tapos meron kang distributive law over scalar multiplication at saka distributivity of scalar multiplication over vector addition at saka distributivity of scalar multiplication over field addition. Associative dapat yung scalar multiplication at saka meron kang identity with respect to scalar multiplication. So we'll see all these properties in action later kapag nag-prove tayo. I think meron ako isang example na ipo-prove natin at least briefly na sila example sila ng vector spaces. Pero ang primary mong kailangan ay meron kang field at meron kang non-empty set. Yes, Rose.
Sir, kapag po yung isa po sa mga conditions ay hindi po satisfied, ano na pong tawag po doon?
Usually, pag gantong mahabang definition, meron pa mga mini structures along the way. Pag halimbawa hindi nyo na-satisfy si property number 7, halimbawa, posibleng may pangalan siya. Pag hindi nyo na-satisfy si property 6, pero lahat na-satisfy niya, posibleng may pangalan siya. Pero for us, pag meron siyang hindi isang na-satisfy, hindi natin siya i-consider. Kasi as far as linear algebra is concerned, hindi enough yung structure na yon para makuha yung gusto nating ideas. So essentially, we'll just say that they are not vector spaces when one of these doesn't hold. Pero wala tayong ibibigay na special name for them. Hindi katulad siguro sa abstract. Sa abstract mo siguro na-compare na halimbawa meron kang group tapos walang additive, walang identity yung group. Anong tawag sa kanya? Semi-group lang, no? Tapos pag semi-group magiging monoid siya. Ano nga ba? Yeah, parang ganon. So kasi meron pa ring magagandang structures na pag mapapag-aralan from a modern or abstract algebra point of view. Pero para sa atin, wala tayong pakialam dun sa mga structures na hindi nakakasatisfy ng 1 to 7. Okay?
Thank you po, sir. Thank you.
All right. Okay, so let's see. Where were we? All right. So yeah, ang additive identity, ang zero vector ay yung literal na zero vector na kilala natin from physics or from calculus. Tapos ang scalar, ang multiplicative identity, which is the identity under scalar multiplication, ay yung real number na 1. Kasi pag yung real number 1 ay may multiply mo sa kahit na anong vector, ang sagot ay yung vector pa rin, right? Kasi ito yung definition ng vector multiplication. So pag meron kang vector v, halimbawa, v1, v2 until vn, nag-scalar multiplication ka dyan ng 1, ang sagot ay v1, v2 until vn pa rin. Hindi na bago yung vector after multiplying by the scalar 1. So yung real number na 1, siya yung scalar multiplicative identity or simply the multiplicative identity of the vector space, while the 0 vector is the additive identity. All right? So, yeah. So, and then you can generalize this, yung konsepto ng pagkuha lamang ng n-tuples, order triples, quadruples, quintuples, basta n-tuples of real numbers or complex numbers together with, this is what we call component-wise addition, because we are adding the components accordingly. So component 1, ina-add natin, components 2, ay pinag-add lang natin hanggang dun sa last components, nagmamatch na component, ina-add lang. So kapag ka component-wise addition yung operation, tapos component-wise din yung scalar multiplication, I mean we are multiplying each component by the scalar at hand, then siya pa rin ay nagiging vector space. Alright? Now, pag pinalitan mo yung R na field, ginawa mo siyang kahit na anong field, siya pa rin ay magiging vector space. So kung si F ay isang field, si F to the N ay isa pa ring vector space over the set of real numbers. Ng operations ay katulad dun sa 26 and 27. So that means in F to the N or in Fn, ang ating vector addition, ina-add lang natin component-wise, tapos yung ating scalar multiplication is also what you call this? It's also component-wise, right? Perhaps I think there's a typo here. Dapat ito ay F. So pag meron kang field F, kumuha ka lang ng n-tuples of that field, then you can get a vector space over the field itself with component-wise vector addition and component-wise scalar multiplication, right? Some examples are the n-tuples of complex numbers and the n-tuples of field elements. Usually ito ay ginagamit sa cryptography and coding theory, and also in algebra, in abstract algebra, madalas itong ginagamit, while complex numbers mas ginagamit sa physics and electromagnetism. Ano? So, doon natin siya pwedeng tingnan. And then, next example ng vector spaces ay set of all matrices. Ano? So, ganito ko siya i-define kung ano yung mga matrix. So, kukuha ko ng isang vector space. So, kita nyo, pinapalaki ko lang ng pinapalaki yung examples ng vector space natin. So, kukuha ko ng isang vector space. Tapos, i-arrange ko lang yung mga elements ng vector space na yon in a rectangular array. So, meron akong, ang mga vector ko ngayon ay vector na ang laman ay mga vector elements arranged in a rectangle. So si V11 ay nanggagaling kay V, si V12 nanggagaling kay V. So everything inside this rectangle all comes from V. Kasi ito yung tinatawag natin na matrix na ang laman ay mga elements ni V. Right? Now, when I define, so I want to create a vector space out of these matrices. So ito yung tinatawag natin ng mga matrix. So pagka-define ko yung matrix addition as component-wise addition, so pag meron akong dalawang arrangements, dalawang rectangular arrangements of numbers, yung nasa first row, first column, i-add ko sa first row, first column ng kabilang matrix. Yung nasa first row, second column, i-add ko rin dun sa nasa first row, second column ng kabilang matrix. Then that's component-wise addition. Yun yung tatawagin kong vector addition. Medyo may misnomer pala, no? Kasi rito ay tinatawag ko rin na vector yung matrices. Kasi ang set of all matrices ay isang example ng vector space. So siguro if that's the case, then I will simply call it as a matrix. Ano? So si V at W, sila ay mga matrices, pero dahil ang set of all matrices ay isang vector space, pwede ko rin silang tawaging vectors. Right? So I add two matrices by adding their components accordingly. Right? And then ang scalar multiplication naman is also component-wise. If I want to multiply the matrix V by a scalar alpha, then I will just multiply all components or all entries in the matrix by the scalar alpha. Okay. Now, the collection of all such matrices, which we will denote by this, is a vector space. All right? So curly M, para malaman natin or para malaman natin right away na siya ay set of all matrices, yung subscript, siya yung dimensions ng matrix. Ilang rows, meron kang M rows, ilang columns, meron kang N columns. So this is basically the set of all M by N matrices na ang entries ay nanggagaling kay vector space V. Okay? So is that okay? So medyo sinisimulan ko nang i-define kung ano yung itsura ng mga matrices. Ano? And then whenever the underlying field, kung importante, yung underlying field kung saan dinidefine yung vector space of matrices, susulat ko siya minsan na ganito. So you can read this as the vector space of M by N matrices with entries coming from the vector space V over the field F, right? Pero the most notable examples of matrix vector spaces that we will consider ay ito, M by N matrices of real numbers over real numbers, and set of all M by N matrices with real entries over the complex numbers. Okay. Tapos kunwari hindi nyo pa nakita yan, what do you think is the additive identity of the vector space of matrices? Ano yung pwede natin tawagin to be the zero matrix? Yes, Jennifer?
Pwede ba zero matrix?
Which is what? Describe me yung zero matrix.
Yung elements ay puro zero.
Yeah, very good. So yung elements ay puro zero. And then madali siyang makita, no? Kasi ang identity lamang naman ay yung i-add mo sa isang vector, in this case sa isang matrix, para walang mabago. So lagyan mo lang ng puro zero yung matrix, tapos i-add mo siya sa isang matrix, hindi niya mababago yung laman ng isang matrix. Alright? So very good. Now, what is the multiplicative identity ng vector space? Halimbawa, nasa vector space ako over the field of real numbers. Ano yung scalar, yung i-multiply ko sa isang matrix? When I say multiply, scalar multiplication ito, no? Ano yung alpha na pwede kong i-multiply sa isang matrix para hindi mabago yung matrix?
One, sir.
Come again, Annabelle?
Is it 1, sir?
Yes, good. So 1 yung multiplicative identity kasi 1, so pag ginawa mo tong 1 times any vector, ang magiging sagot ay 1 times vector element, yung 1 naman, multiplicative identity yan under usual multiplication, ano? So hindi niya mababago yung laman ng matrix. So good. So those are the, and then yung properties, associativity, commutativity, distributive laws, associativity ng scalar multiplication, ay madali siyang i-check, pero matrabaho. Ano? So I'll skip the proof of that. Other examples, pag meron kang vector space V, yung V infinity, ito naman ay set ng mga infinite sequences, vector space din yan. I mean, hindi na siya n-tuples. Halimbawa, meron kang 1, 0, 0, 0, 0, 0, 0, forever. Ito ay isang infinite sequence ng elements ng isa tong example ng element ng isang infinite sequence. Pag kinuha mo lahat ng possible infinite sequences sa isang vector space, siya ay isang vector space pa rin. Alright? Ang identity rito ay yung infinite sequence na puro zero yung laman, tapos ang scalar multiplicative identity naman ay 1 pa rin. Okay? So, pwede pa rin siya. Parang extension lang to ng mga n-tuples. Ngayon, pinapayagan natin na infinitely many yung laman ng vector spaces. Okay? Now, ito yung isa sa mga medyo masaya na example ng vector space, yung example 9. Sa example 9 ay medyo kakaiba kasi hindi na to yung tulad nung nakikita natin dati na puro na puro numbers lang yung laman. Pwede pala tayong mag-consider ng isang vector space or gumawa ng isang vector space using equations 29 and 30. So in this example, we're considering a non-empty set capital A, and it doesn't matter kung ano yung laman ni capital A. Tapos, kukunin natin yung vector space consisting of the power set of A. Familiar pa kayo sa power set of A? Or kung hindi, magbibigay ng isang specific example. But this is called the power set of A. Yung power set ni A, laman niya lang lahat ng subsets ni set A. So that power set of A can constitute a vector space over Z2. Medyo kakaiba yung example, no? Pero how do we define vector addition? I will define vector addition this way. Pag meron akong vector X, i-add ko siya sa vector Y. Pero anong itsura ng mga vectors natin dito? Ang mga vectors natin dito ay mga sets. Kasi sila ay mga subset ni capital A. Na pag meron akong set X na vector, set Y na vector, at gusto kong i-add itong dalawang sets na to, or itong dalawang vectors na to, ganito yung gagawin ko. Kukunin ko yung union nila, tapos tatanggalin ko doon yung intersection nila. So minus, this is a set minus. So the intersection. So in Venn diagrams, kung ito si X, tapos kung ito si Y, so ang X union Y ay syempre yung X at saka Y, no? Yung dalawang bilog. Pero tatanggalin natin yung intersection nila. So yung X plus Y ay bale ito. Oops, sorry. Nawala yung... So ito si X, ito si Y, ang X plus Y ay ito. Lahat ng nakay X, lahat ng nakay Y, pero tatanggalin natin yung mga elements na nakay X at saka Y na parehas. So hindi kasali ito, yung nasa gitna. Right? So that's how we define addition, vector addition. And then scalar multiplication is defined this way. Ang field ko lang ay Z2. So dalawa lang yung scalars natin, 0 and 1. Now, if we multiply a set, a vector X, by 0, ang sagot ay empty set lang, by definition. Tapos pag naggawa ko ng 1 times a set, ang sagot ay yung set lamang na yon. Alright? So, mas simple yung vector, ay yung scalar multiplication kasi dalawa lang naman yung posibleng scalar. And the answer for scalar multiplication is either the empty set o yung set lamang na yon. So siguro let's look at one particular example before we prove some properties of vector spaces. Okay. Halimbawa, ang set A ko ay ano bang gusto yung set? Yung maiksi lang kasi lalaki yung vector space, ano? Siguro apple, banana, and orange, halimbawa. Halimbawa, ito yung set A ko. So, ito yung set A natin. And that's fine because the example just told us to have a non-empty set A. So, okay lang yan kahit ano yung laman niya. Tapos, kukunin natin yung mga subsets ni A. So, that would be the power set of A. So, yung power set ni A, ang laman niya lang ay lahat ng posibleng subsets. So, ito yung laman niya. So, una, empty set. Subset siya ni set A. Tapos yung mga subsets na tigi-tigisan ng laman. So, apple, set containing apple, set containing banana, then set containing orange. Right? And then, yung mga dalawahan naman yung laman. So, set containing apple and banana. Then set containing apple and orange. Then set containing banana and orange. And then yung tatluhan naman yung laman, yung mismong set A na. Yung set na apple, banana, and orange. So meron tayo ditong 8 vectors. Yung 8 nating vectors ay empty set containing apple, set containing banana, set containing orange, set containing apple and banana, set containing apple and orange, set containing banana and orange, and then the set containing apple, banana, and orange. Tama ba yan? 8, 1, 2, 3, 4, 5, 6, 7, 8. Yes. Kasi ang formula sa cardinality ng power set ay 2 to the n, where n is the number of elements of A. May 3 elements sa A, so yung power set niya may 8 laman. At bawat isang naka-highlight, yung 8 na yon, sila yung mga vectors natin. Right? And then let's play. Sabi natin yung x plus y ay equals x union y minus x intersection y. So let's solve what? So siguro solve natin yung vector apple. Halimbawa plus vector apple orange. So para na makita natin kung paano nag-work yung vector addition. Ano? So by definition, this is what? So i-solve muna natin to. So ano yung x union y? Kung ang x ko ay set containing apple at ang y ko ay set containing apple and orange, ano yung x union y? Tandaan niyo pa ba yung union?
Orange, sir.
Union muna. Final
Apple
answer
and orange,
binigay
sir.
mo, no?
Apple and
Yeah,
orange.
thank you. Yeah, thank you, Ian and Annabelle. So, yung sagot kanina, sino ba yun? Si Rose ba yun? Ay final answer na yata. So, kunin ko muna yung union. Step by step muna tayo. So, kunin ko yung union. So, itong union na yan ay pagsasamahin ko lang yung elements nila. So, I'll have apple and orange minus yung intersection. Anong intersection nila? The one that they have in common, right? May apple
Apple,
dito,
sir.
may apple din dito. Thank you. Yeah, thank you. That's right. So apple yung intersection. Apple comma orange minus apple is set containing orange. Tama? Ito yung sinasabi kanina ni Rose yata. So yeah, this is a set containing orange and you see that orange is one of the vectors. Right? Kasi yun naman yung kailangan eh. Pag nag-add ka dapat ng dalawang vectors, dapat ang sagot ay vector pa rin. Right? Now, what could be, say, empty set plus set A? What do you think? So, final answer na. Baka kaya nyo na itong i-mental. Empty set ay walang laman, set A laman niya lahat. Ano yung empty set plus A? Yes. Sino yung
A
set?
po, A.
Yeah, Jennifer and Annabelle, right? This is A. Good. Yeah. Kailangan nyo lang i-perform yung set operation. Ano? What do you think is A plus A?
Empty set.
Empty set ba? Let's see. Yeah, that's right. It's empty set. Yeah, kasi bakit empty set? Sige, check nga natin. So, magkakaroon ako ng A union A minus A intersection A. This is A minus A. Ang sagot ay empty set. Good. How about, say, apple banana plus set containing apple banana? Tingnan, saan to equal? Teka, kung kailangan nyo mag-compute.
Empty set, sir.
Sino yan? Ian? Yeah, empty set? Good. Empty set siya. Parang bilis nyo mag-compute ng, ng symmetric. Ano ba tawag dyan? Symmetric difference nga ba tawag dito? Kalimutan ko ang tawag dito. May isang term dyan eh. Yeah, but that's correct. That's going to be the empty set. So you see here, we can have a vector space with crazy operations like this, not even numbers. Now, try natin yung scalar multiplication. Say 0 times A. What is 0 times A?
0.
Hindi 0. Remember, ang scalar multiplication, dapat vector yung sagot.
Empty set.
Yeah, great, Jennifer. This is the empty set. 0 times apple banana.
Empty
Is
set.
it empty
Empty
set?
set, sir.
Empty set, right? Baka lang nakalimutan ng iba na dinefine ko explicitly yung multiplication kanina this way. Pag meron na, pagka kahit anong set, i-multiply ko ng 0, ang sagot laging empty set. Tapos yung isa pang posibleng scalar multiplication, 1 times the set, ang laging sagot ay yung set pa rin na yun. Alright? Now, you can check the other properties, yung associativity ng addition na to ay medyo mahaba lang i-prove, pero kailangan nyo lang maglaro with distributivity of union over intersection and vice versa. Commutativity of addition is fine, madali lang siya. How about additive identity? Anong additive identity ng vector space na to? Or what is the zero vector?
Empty set, sir.
Is empty set. Yeah, that would be the empty set. Paano natin ito ipoprove? Okay, paano natin ipoprove na si empty set ang zero vector? Kailangan lang natin ipakita na pag inad ko yung empty set sa kahit na anong set, ang sagot ay yung set pa rin na yun, right? So that's how you prove something is the zero vector. So I will let, say, X be an element of the vector space, right? Kuha ko na isang set X na arbitrary na nanggagaling dun sa ating vector space. Then we compute X plus the empty set and hope that the answer is the set X pa rin, right? Do you follow, guys? So ganito tayo nagpo-prove, di ba, ng pagiging zero vector. I-add ko lang siya sa lahat ng elements, so sa isang arbitrary element ng vector space and hope that I'll get the set, the vector space, the vector X back. Tama? Right, and then by definition, ang addition na nandito sa vector space na to ay X union the empty set minus X intersection the empty set. So X union the empty set is X minus X intersection the empty set is the empty set. So this is the empty set X. This is the set X. So meaning for any set X added to the to the empty set, the answer will be the set X pa rin. So indeed, we have proven that the zero vector is the empty set, right? Now, what is negative X? Next question. So anong additive identity, anong additive inverse ng isang set X, ni set X? So again, you will be looking for ano dapat yung i-add ko kay X para yung sagot ay empty set.
Positive X po?
Positive X.
Or the opposite of, yun nga, positive pa rin.
Pero in our case, halimbawa, ano yung additive inverse ni Additive inverse ni apple banana? Halimbawa, what is the inverse? What is the inverse of ano ba yung example ko na kanina?
Sir,
apple banana.
Sir, just the set itself po.
Yeah, great, Rose. Nice observation, right? So it's really the set itself pa rin. Katulad na di ba, ang additive inverse ay kung ano yung i-add mo sa isang vector para makuha yung additive identity. So in our case, ano yung set na i-add ko sa isa pang set para makuha ko yung empty set? And kanina sa examples natin, nakita natin ng apple banana plus apple banana ay empty set. A plus A ay empty set pa rin. So that probably prompted Rose to think na ang inverse ng isang vector ay yung sarili niya. Right? Because from these two examples, that seems to be the case. Now, kailangan nga lang nating i-prove na totoo yon. Na ang so the answer here is apple banana. And here we are claiming, or si Rose, kinlaim niya kanina na the inverse of X is itself, right? So if you want to write a proof for this, So kailangan ko lang ipakita na x plus x is equal to the empty set, right? So we'll just let x be an element of the vector space, then compute x plus x. And by definition, x plus x is x union x minus x intersection x. Ang x union x ay x. Ang x intersection x ay x din. Tapos x minus x ay empty set, right? So therefore, we can say that the additive identity of x, which is written negative x, is equal to itself. Okay? Is that good? Any questions? Bis yung nahulaan, yung additive inverse. Kala ko magtatagal tayo dito eh. Any questions?
None, sir.
Yeah, thank you, Rose. How about the others? Okay lang? Medyo kakaiba, no? But I hope you're getting the hang of it. Medyo mahirap talagang bitawan yung mga natutunan natin dati, lalo na kung kakaiba yung mga ipapalit natin sa kanila, right? Now, yeah, after these examples, we can now look at some properties, elementary properties of vector spaces. At ito ay analogous dun sa proposition 1 natin before that talks about properties of fields. So in this proposition, we are considering a vector space V over a field F. Tapos si little v, w, sila ay mga elements ng vector space. Si alpha ay element ng field. Si E yung zero vector. At saka si 1 yung multiplicative identity. Alright? Tapos meron tayong iba't ibang mga properties. Now, property number 1 ay if Z is a vector that has the property V plus Z equals V for all elements of V, then Z must be the identity. So essentially, this is just telling us that the identity is unique. The identity of the vector space, the additive identity of the vector space is unique. Kasi pag nakakita tayo ng isang vector Z, na pag inad ko sa kahit na ano pang vector V, ang sagot ay vector V palagi, then Z is always, necessarily is the identity vector or the zero vector. Kasi nga, this is tantamount to saying that the zero vector is unique. Right? Property number 2, pag meron kang scalar times the zero vector, ang sagot laging zero vector pa rin. Right? Tapos ang additive inverse ng identity times a vector ay additive inverse ng vector. Property 4, additive inverse ni alpha times vector ay equals sa additive inverse ng alpha v, which is also equal to alpha times the additive inverse of the vector. And then the additive inverse of the additive inverse of a vector is itself. Yung alpha times v ay equals sa additive inverse ni alpha times times additive inverse ni v. Tapos ang additive inverse ng v plus w ay additive inverse ni v plus additive inverse ni w. And you can distribute actually madali lang tong part 8. It's just another version of the distributive property, right? Because here you can just say that you have alpha times v plus negative w. Then this will be equal to alpha v plus alpha times negative w by the distributive property of scalar multiplication over vector addition. And then by property what? By property 4, this is equal to a alpha v minus alpha w. Right? So yun yung proof ng property number 8. And then property number 9, if alpha v is equal to E, then either, parang ito naman yung zero property ng vector spaces. Pag meron kang scalar times a vector, at yung sagot sa scalar multiplication nila ay zero vector, then either si V ay si zero vector or si alpha yung zero ng field. Alright, so laging parang ito yung ano natin, A times B equals 0, either A is 0 or B is 0. Ganun din sa field. Pag nag-scalar multiplication siya tas ang sagot ay 0 vector, either yung vector ay 0 vector o yung scalar ay yung 0 scalar. Okay? Now, the proofs are here. I don't know. Meron bang mahirap dito na proof? Na kailangan i-prove? I think the proofs here are self-explanatory, unless you guys have questions about it. The proofs are very similar to the proofs we did in proposition number 1. Okay. So is it okay if we just skip the proofs here and then you can just read them? Yeah, you can read them on your own time. Sasabihan niyo ako next time kung may tanong kayo doon, ano? Kasi when I wrote the proofs, I tried to include all the details there. So it will also be a good exercise for you to read proofs and then mark up whichever parts are not clear to you, and then let me know when we meet again on when will we meet again? Kailan nga tayo nagme-meet? Wednesday, no? Wednesdays and Saturdays. So on Wednesday, let me know if there are any questions about it. All right, so now let's go to the fourth definition. The fourth thing we are defining here would be a subspace. This is very similar dun sa konsepto natin ng subfield. So kung ang subfield ay isang subset ng isang field na field din, ang isang subspace ay isang subset ng isang vector space na vector space din. Right? So formally, you consider a vector space V at sa isang field F. Pag kumuha ka ng non-empty subset W ni V, alright? So non-empty subset siya, kung ito si V, kukuha ka dyan ng W sa loob niya. Tapos kung si W ay isang vector space din, under the same vector addition and scalar multiplication, then we say W is a subspace of V. Okay, so isa lang siyang mas maliit na vector space. But again, the important thing here is that the vector addition and scalar multiplication for W should be the same as V. Okay, hindi kayo pwedeng magbago ng operation. Now, let's see what is a good example here. Okay. Okay, now, whenever checking if something is a vector space, usually everything just boils down to a couple of things. Ano? First is closure. Kapag ka kumuha ka ba ng dalawang elements nung subset, ang sagot ba ay nandun sa subset pa rin? So usually that's one question that we usually ask first before checking additive identity and multiplicative identity. Kasi usually lahat naman ng properties ay mai-inherit lamang nung vector space mula dun sa parent vector space. So makikita natin mamaya yung tinatawag natin na compact criterion for checking for subspaces. Okay, now, paano natin sine-check yung closure? So halimbawa, consider ko si R3. Set of all triples of real numbers. Tapos kumuha ko ng subset niya. Yung subset na i-consider ko niya ay set of all triples. Alright? So nagagaling siya talaga kay R3. Pero dapat ang product ng entries ay equal kay 0. Okay. So, yan yung subset G na i-consider ko. Now, before even thinking whether G is a vector space on its own, we need to check closure first. Bago nyo i-check yung mga properties ng pagiging vector space ni G, kailangan i-check nyo muna closed ba siya under usual addition and scalar multiplication, right? So, madali siya makita na closed siya under scalar multiplication kasi pag meron akong ABC na element ni G, ano nga ibig sabihin ng pagiging element ni G? Yung product ng mga components ay equal lamang kay 0, right? Pag nag-multiply ako sa kanya ng scalar alpha, right? Kasi gusto kong i-check kung closed ba siya under scalar multiplication. So mag-multiply ako ng scalar alpha kay vector ABC, right? And this is just scalar, this is just component-wise addition. So ito yun, component-wise scalar multiplication. So alpha A, alpha B, alpha C. Alam kong element pa rin siya ni G kasi pag pinag-multiply ko yung alpha A times alpha B times alpha C, ang sagot ay alpha cubed ABC. Pero alam ko yung ABC ay equal kay 0, so yung alpha cubed times 0 ay equal pa rin kay 0. So itong scalar product na to ay na kay G pa rin. Kasi ito times ito ay equal rin kay 0. Okay? So we can say that G is closed under scalar multiplication. Right? Kasi pag nag-scalar multiplication ako ng element ni G with any scalar, ang sagot ay na kay G pa rin. Kaya lang, si G ay hindi closed under addition. Kasi meron akong pwedeng ipag-add na dalawang elements ni G nang sagot ay wala kay G. You can come up with various counterexamples, pero ang napili kong counterexample, ang binigay kong counterexample dito ay si 101 at saka si 110. Si 101 ay na kay G kasi yung 1 times 0 times 1 ay equal kay 0. Yun yung requirement para mapalagay ka kay G, right? Yung 1 times 1 times 0 ay 0 din, so pasok siya kay G. Pero pag inad ko na itong dalawa na to, 101 plus 110, ang sagot ay 211. Pero yung 2 times 1 times 1 ay 2, hindi na equal kay 0, so this guy doesn't belong in G. Kasi para mag-belong ka kay G, dapat ay ang product ng laman mo ay equal kay 0. So without checking associativity, commutativity, additive inverse, additive identity, identity under scalar multiplication, distributive loss, and all, masasabi na kagad natin na si G ay hindi subspace ni R3. Kasi si G ay hindi closed under vector addition. Alright? So wag nyo nang ubusin yung oras nyo pag-prove nung mga bagay na yon, nung properties 1 to 7 ng definition number 3, kung hindi naman talaga closed under the under vector addition or under scalar multiplication yung subset. All right? Is that good?
Sir, bakit po siya hindi naging close po under addition? Considering na yung answer ay 211.
Yeah. Para maging close ka under vector addition, dapat yung sagot after you do the vector addition, dapat nandun sa set G pa rin. Right? So it's crucial that you remember ano yung definition ni G. Makakapasok ka lang kay set G kapag pinag-multiply mo yung mga entries, ang sagot ay 0. Right? So obviously, si 101 ay na kay G. Kasi ang 1 times 0 times 1 ay 0. Si 110 ay na kay G kasi ang 1 times 1 times 0 ay 0. Pero pag pinag-add ko na silang dalawa, ang sagot na ay, tama ba pagkaka-add ko? Yes, 211. Alright? Pero ano ang 2 times 1 times 1? Ang 2 times 1 times 1 ay 2. Hindi 0. So, ibig sabihin, wala siya kay G. So, nakakita tayo ng dalawang vectors na ang sum ay wala kay G. So, ibig sabihin, si G ay hindi closed under addition. At wala na siyang chance maging subspace. Right? Is that clear?
Clear na po, sir.
Okay, yeah. That's good. Other questions? So usually, yun muna talaga yung chine-check. Closure under addition and multiplication. Kasi pag walang closure, wala nang chance maging subspace. All right? Now, okay. Yeah. Example 10, it talks about the vector space of all functions. All right. So, tingnan natin. So, we consider a vector space over a field F. So, meron na tayong vector space V na over the field F. Tapos si omega ay isang non-empty set. And then, dun yata sa homework, dun sa homework, may item doon na pinapaprove ng set of all functions from omega to v is a vector space, right? So I will not prove it here, pero yung set ng lahat ng functions mula kay omega papunta kay v ay isang vector space. Ang vector addition ay ganito. Ang function f plus function g ay equals sa function na fx plus g, f of x plus g of x, and ang scalar multiplication ay yung usual scalar multiplication ng function. Alright? Medyo may konting abuse of notation dito. Yung addition dito ay addition of functions. Ito ay addition of function values. Right? So yung function f plus function g ay equal sa function na ang ginagawa ay pinag-add lang yung function value ni under f at function value under g ni x. Alright? Yeah. Tapos, gusto kong mag-consider ng isang subset. Ng isang subspace. Alright? Kasi yung buong set ay set of all functions. Pero kung i-consider ko lang yung mga functions na ganito yung itsura. Functions pa rin, pero dapat yung function ay g of lambda ay equal kay identity element, kay zero vector o kay zero function. Right? So here, I am considering a non-empty set lambda of gamma, of omega. Right? So, i-define ko sa set G to be set lang ng lahat ng functions na ang function value ng mga members ni lambda ay equal kay zero vector. So, kinukuha ko lang yung mga function na ina-assign lahat ng elements ni lambda dun sa zero vector. And I want to prove that this is a subspace of F. Right? Now, as I've mentioned before you check the other properties ng pagiging vector space, we need to check first closure. Alright? So, kukuha ko ngayon. So, dalawang closure yung i-check natin. Closure under addition and closure under scalar multiplication. So, to prove them, I'll get two elements of G. Kukuha ko ng dalawang elements ni G. Tapos, i-consider ko yung F plus G at saka yung alpha times F. Gusto kong ipakita na lagi silang na kay G pa rin. Paano kung mapapakita na sila ay na kay G? Dapat yung function value ng mga elements ni lambda ay equal sa zero vector. Okay? So let's take a look at F plus G. Tapos kukunin ko yung function value ni lambda. So F plus G of lambda, by definition of vector addition, is just F of lambda plus G of lambda. Pero saan equal si F of lambda? Si F of lambda ay equal lang kay E. Bakit? Kasi si F ay na kay G. Napapasok lang ang isang function kay G kapag ka ang function value ni lambda ay E. So ang function value ni lambda under F ay equal kay E. Tapos dahil si G din ay si little g ay na kay curly G, so ibig sabihin ng G of lambda ay equal din sa zero vector. Good? So this guy will be a zero vector plus zero vector. E ang sum ng dalawang zero vector ay equal din sa zero vector. Right? Kasi nga ito ay additive identity under some vector addition. So that will be E. So that means F plus G ay na kay G din. Kasi ang function value ni lambda ay equal rin kay E, which is the requirement for functions to be in capital G. Okay? And then scalar multiplication naman. Tingnan niyo yung alpha f of lambda. Our prayer is that alpha f of lambda is equal to the zero vector E. Right? How do we do it? Well, by definition of scalar multiplication, this guy is just alpha times f of lambda. But what is f of lambda? Since f belongs in G, f of lambda must be equal to 0, the zero vector, right? So that will be the zero vector E times alpha. Alpha times the zero vector is equal to the zero vector. Sabi ng proposition, let's see which proposition is that. Proposition 2 point what? That's proposition 2.2. Scalar times 0 vector equals 0 vector, right? So that's what was used here. Go down, yeah. Scalar times 0 vector, 0 vector, right? So that means alpha f also belongs in G kasi ang alpha f ay equal sa 0 vector, right? So that means we can say that G is closed under vector addition and scalar multiplication, okay? And then properties 1, 2, 4, and 6, as well as 7, na-inherit lang siya mula doon sa pagiging vector space ni curly F. Kasi si curly G, if you remember, curly G is just a subset of curly F. So yung associativity ng vector addition, commutativity of vector addition, property 5 is this distributive loss, property 6 is the associativity of scalar multiplication, property 7 is the existence of multiplicative identity insofar as scalar multiplication is concerned. They are just all inherited mula dun sa properties ni F being a vector space. Kasi kung totoo siya dun sa buong F, then definitely totoo yung 5 properties na yan kay G na nasa loob lamang ni set F. Ha? Now, meron na lang natitira. Ano na lang yung mga natitira? Existence of additive identity at existence ng additive inverse. Right? Pero madali lang yun kasi yung zero function, I don't know kung sino yung mga nagsagot sa inyo ng item pertaining to curly F being a field dun sa homework number 2. So kung nagawa nyo na yun, good for you. Kung hindi pa, magkakaroon kayo ng hint dito kasi yung zero function is just the function that maps everything to the zero vector. Yan yung zero function. Yan yung zero vector kay F. Pero itong zero vector na to kay F, nandun din siya kay curly G. Kasi pag pinlogin mo si lambda kay Z, ang sagot ay E. Kasi kahit anong omega ang i-plugin mo kay Z, ang sagot ay E. Sa pag ginawa mong omega equals lambda, E pa rin yung sagot. Kasi si zero function, lagi niya lang namang minamap lahat ng elements kay zero vector. So ibig sabihin si zero function ay na kay G din. So ibig sabihin, nasa-satisfy yung property 3 na merong additive identity yung vector addition. Merong additive identity si set G. Kasi yung additive identity ni set curly F ay na kay curly G din. Okay? And then, so kulang na lang ay existence ng additive inverse. So dapat pag meron kang isang element ni curly G, dapat magkaroon din siya ng additive inverse kay curly G. Well, sir, hindi ba yung guaranteed? Hindi siya laging guaranteed. Kasi vector space nga si capital F. So alam ko merong additive inverse si G kay capital F. Pero ang gusto kong mangyari ngayon ay si G dapat na kay curly G din. Gusto ko yung additive inverse ni G, yung additive inverse ni little G ay dapat na kay curly G din. Kasi pag nandun lang siya kay curly F, posibleng nasa labas siya ni curly G. Right? Pero madali lang siyang pakita kasi alam ko na ang additive inverse ng isang function G ay si negative G. Gusto ko na lang ipakita na si negative G ay na kay curly G din. Right? Pero madali lang siyang ipakita kasi ang negative G of lambda ay equal kay negative 1 times G of lambda. By definition. And then G of lambda is the identity. Right? And then you will have negative 1 times 0 vector equal yan kay 0 vector. So ibig sabihin, yung additive inverse ng isang element ni little g ng isang element little g ni curly G ay na kay curly G din. Right? And so that means subspace ni curly G, subspace ni curly F si curly G. And usually we write it this way, although hindi ko naman yata ito ginamit dito, Pero ito yung ginagamit natin para sa subset, para sa subspace. Kasi napakita natin na si curly G ay isang vector space on its own. And curly G is also a subset of curly F. Kaya siya naging subspace ni curly F. Okay? Any questions? Or medyo nakakalito kasi may curly G na, may small g pa, and so on. But if that's a little obscure for you, you can read the modules again in details just to be accustomed with those kinds of notations. So no. All right, maybe the last thing I want to do today is show you the compact criterion, which is theorem number 3. Naghihingalo na rin kasi yung yung battery nung pencil ko, ano. Pero anyway, as you have seen in the proof of G being a subset of F, nag-rely lang tayo actually sa closure, all right? At saka, yeah, nag-rely lang tayo sa closure, existence ng additive identity, at saka existence ng additive inverses, all right? But, and then we just mentioned that all other 5 properties of definition 3 were satisfied by inheritance. All right. So we can make sort of a compact criterion para mapadali yung pag-check kung siya ay subspace o hindi. And that is theorem number 3. So you can call this the compact criterion. For subspaces. So if you want to show that a subset is a subspace of a vector space, hindi nyo na kailangang i-check yung closure plus the 7 properties. All right. All you need to do is to check yung closure under vector addition and scalar multiplication. All right. So yun na lang yung gusto nyo ipakita. So kumuha ka ng dalawang elements si W. Pakita mo na yung V plus W ay na kay W din. At yung alpha V ay na kay W din, then you get yourself a vector space. But sorry, you get yourself a subspace. But what theorem V requires, dapat meron kang vector space to begin with, tapos si W ay non-empty subset ni V. Tapos kailangan mo na lang ipakita closed si W under the vector addition and scalar multiplication. And if that's the case, no need to check all other properties. You get yourself a subspace. Okay? Sa homework 2 nga ba? Or pero mukhang hindi nyo pa ini-start yung homework number 2, ano? Busy pa kayo sa homework number 1. But if in homework 2, there's a question about showing one thing is a subspace of another, use theorem 3. You don't have to check all the 7 properties plus closure. All you need to do is to check closure. Closure under vector addition and scalar multiplication, and then by inheritance and a little bit of quick arguments, magpa-follow na siya kagad na isa siyang subspace. Alright? So ang kailangan nyo na lang talagang ipakita para maging subspace siya ay closure under vector addition and scalar multiplication. Okay? Alright. And then siguro next time na lang, we'll be showing how to create subspaces for certain vector spaces, all right? And some important subspaces. Pero ngayon I think it's fine. Medyo marami na tayong na-tackle ngayon. We have tackled the definition of vector spaces, some examples, elementary properties of vector spaces, and the concept of subspaces. So for next time, we'll be talking about how to create subspaces and some important subspaces. Okay. So do you guys have some questions? Or concerns?
None, sir.
All right. Thank you, Jason. So if there are no questions, thank you guys for joining me today. I am thinking Wednesday by holiday. I'm thinking of what's the next meeting for us. Oh, but Wednesday is a holiday.
Holiday po ang Wednesday, sir.
Yeah, so Anong oras yung ano nyo? Yung abstract algebra nyo ng Tuesday?
7 to 9 po, sir.
7 to 9 din. Kawawa naman kayo kapag ka nag-ano tayo, no? Kapag ka nag-meet pa ako sa inyo ng Tuesday. Let's see. How can we do this? All right. So I'll think of another way to schedule our next meeting, because supposedly we'll be meeting on Wednesday, 7 to 9, but that is a holiday. Unless you guys would like to meet on a holiday. So magpa-poll na lang siguro uli ako para malaman ko kung gusto niyo makipag-meet ng Wednesday or some other day aside from the holiday, because I know you want to spend the holiday with your family or rest for the holiday. I don't want to take that away from you. So I'll be looking for another way. Pero if you are all willing to do it on a Wednesday, then that's also fine with me. So I'll send a poll na lang, pero pag-isipan ko muna ano yung alternative. All right? Yeah, and then until then, please work on the homeworks. Let me know if there are some other questions. Yeah, Sol.
Sir, ano po yung deadline natin sa homework 2?
Sa homework 2 ay TBA pa. So to be determined pa.
Okay,
So,
thank you, sir.
yeah, next time ko sabihin para mas substantial na yung na-tackle natin about homework number 2 before we have the deadline. But please start working on it. I believe you can answer some of the questions there. So, ilan ba pinapasagutan ko sa inyo? I forgot how many items I asked you to do for homework number 2. Pero kumusta pala yung homework 1? Masyado bang marami? So,
Sir,
homework
I appreciate, sir, yung may mga options kami kung ano po yung sasagutan po namin.
Oh, yeah. Thank you. Pero sabihan niyo ako pag sobrang madami, pwede pa nating bawasan, ano? Pero yeah. In homework number 2, 4 yung sasagutan. I can probably bring it down to 3 problems na lang. Para medyo baka na-shock kayo dun sa homework 1. So I'll give way for homework 2. Sige, let's try 3 items na lang for homework number 2. But you can try to answer more problems, right? The more things you answer, the better. Pero ang ipapapasa ko na lang ay 3 para medyo mabawasan yung kailangan yung gawin. No? That especially we'll be going into a holiday week. So para ma-feel nyo naman na meron pa rin tayong holiday. So yeah. So I'll post probably on Monday, I'll post a poll asking you when do you want to meet in light of the holiday. But until then, please work with the homeworks. Finish up homework 1 or start doing homework number 2, and then we'll meet again. All right. So thank you guys for coming. See you next week. Bye.
Thank you po,
Thank
sir.
you, sir.
Thank you, sir.
Thank you.
Bye-bye.
Thank you, sir.